Okay, now there are operations on matrices and then properties of matrices based on those. So algebra of matrices or the matrix algebra basically. So first one is the addition. Okay, we are now, when we say matrices, there are two matrices. So equality of matrices and then we'll go for addition. Equality of matrices, when are two matrices A and B said to be equal? Anybody? A and B are two matrices. Okay, when are they said to be equal?
When determinants are same, I think.
No. No. When are two matrices said to be equal?
When Aij equals Bij.
Okay, and
When its
Aij,
order and elements are equal.
yes, very good, very good. Orders of A and B must be equal for first step. Then first this condition must be satisfied. Second condition is Aij will be equal to Bij for all I comma j. This notation is for all. Okay, for all, for every. All right, so when I write these notations, so Aij is equal to Bij for all I and j. Okay, this is the equality of matrix. So yeah, Amit, I'm muting you because of this noise. Yeah, now just look at this. This is 2 1 2 0 3 0. This is 2 1 2 0 3 0. Elements are the same, but the matrices are not equal because the orders are different. All right, example 2, the orders are different. Example 2, orders are same, elements are different. Okay, now it does not matter if you know A22 and B22 are equal, like these two are same. Every element must be equal. Every element must be equal. Two matrices are said to be equal only when they are of the same order and the same elements. So A If it is 2, 1, 0, 5, B also has to be okay. If B is X, Y, Z, W, this implies X equal to 2, Y equal to 1, Z equal to 0, and W equal to 5. So this is about equality of matrices. Okay. Next is the operation of addition of matrices, or the matrix addition. When can two matrices be added? Answer. When can two matrices be added?
Same order.
Yes, very, very good. So matrix A, A and B are conformable for addition. We write like this. A and B are conformable for addition if their orders are same. Only then you can add. So see, matrix A and B will give rise to matrix C, provided the A and B matrices are of the same order. So the notations we are writing like this. We are writing notations like this. Now when you see here, Cij is equal to Aij plus Bij. I am purposely making this notation form of matrices. There's a reason for it, because you have to get used to it, because in logic and some reasoning questions, these kinds of things are important. And of course, when you write programming, you have to be very clear of these I's and J's in arrays. So for every I and J, okay, Cij is equal to Aij plus Bij. So let us say there are two matrices. Matrix A is 2, 0, 4, 1, and matrix B is 3, 1, minus 2, minus 4. So when you add them, each element, the corresponding elements get added. 2 plus 3 is 5, 0 plus 1 is 1, 4 minus 2 is 2, 1 minus 4 is minus 3. So these corresponding elements get added. All right. That is matrix addition, which we know. It is not a new thing for us. Now, these have properties. Yeah, these questions are important. Whenever you get properties, sometimes suddenly a tricky, simple but a tricky question is asked on properties, especially transpose and inverse and so on. So matrix addition is commutative. Means what? Means what? A plus B is equal to B plus A. Okay, it is associative. Means if you have three matrices A, B, C, you can first add A and B and then add C, or you can first add B and C and then add A. They will be the same, they'll be equal, associative. Then additive identity. What is the identity of additive identity? A plus null matrix so null matrix is the identity matrix. So null matrix is the additive identity. All right. Then inverse, additive inverse. What is the additive inverse of A? Anybody? What is an additive inverse of a matrix? No one?
Changing the sign of a particular number.
All right. If to a matrix you add another matrix such that you get a null matrix, all right, that means first of all B and A should be of the same order. Okay, then B is called the additive inverse of A. So B is nothing but minus of A. Multiply every element of A with a negative sign. Okay, and then of course the cancellation laws hold true. Cancellation laws, if A plus B is equal to A plus C, this implies B equal to C. So we can just cancel off A, and suppose we have here, okay, A plus C is equal to B plus C. This is left cancellation law, the first one. The second one is the right cancellation law. Okay, so this is about additions, addition of matrices, how matrices are added. So this is just a review what we have done. There'll be simple questions on that. I'll give you some examples once we finish multiplication. Then multiplication, this is addition of matrices, equality of matrix over, then addition of matrix, then multiplication of matrix. Okay, the whole reason multiplication is defined the way it is defined is to accommodate for the simultaneous equations, that which we discussed in the right in the beginning of the class. All right, this one, the simultaneous equations so that we are able to write the equations in this form. And then we solve. For that reason, multiplication of matrices is defined like this. The whole idea of developing matrix algebra is to solve simultaneous equations. So if very important, if A is m cross n or m cross p, and matrix A, and B, matrix B, is of the order p cross n, then we define A into B. Okay, A m cross, I will write like this. That this will be equal to C m cross n. So remember, in matrix multiplication, the left matrix is m cross p, the right is p cross n, and you omit the common. Omit the common. That means the rows and the columns. Then m cross n will be the order of the product. Order of the product. Okay. Now A and B are said to be conformable for multiplication if, tell me in words, when can two matrices A and B be multiplied? Anyone?
If m is equal to n.
No.
When the columns of the first matrix equal the rows of the second matrix.
Yes. If the columns of A, the number of columns, actually just the number of columns, if the number of the columns of A is equal to the number of the rows of B. That too for A into B, not for B into A. This is for A into B. Okay, this is conformability of multiplication. So here is the trick actually. So this is so simple. We'll take a simple example. 2, 4, 1, 5 multiplied by 3, 0, 2, 1, let us say. So this is A, this is B. So what we do, row multiplied with the columns. So the answer will be the first row elements get multiplied with the first column elements to give the first row, first column element of the product. So 2 into 3 plus 4 into 2. 2 into 3 plus 4 into 2. The first row second column and column element of the product will be 2 into 0 plus 4 into 1. 2 into 0 plus 4 into 1. Then the second row, first column element, 1 into 3 plus 5 into 2. And then the last row, last column element, 1 into 5, sorry, 1, 5 multiplied with 0 and 1. So 1 into 0 plus 5 into 1. So the product is 6 plus 8, 14, 4, 13, 5. So this is how matrix multiplication is defined. Okay. Now, properties of multiplication. Here, likely questions. Okay, first addition was commutative. Property multiplication is not commutative. Okay, AB is not equal to BA. Many times BA may not exist. All right, BA may not even be defined. If they are not square matrices, then AB, BA may not be defined also. Okay, so in fact, we do the other way around. We do this multiplication here. Just now we did AB, now we do BA. 3021 multiplied with 2415. The product is 3 into 2, 6 plus 0, 6. 3 into 4, 12 plus 0, 12. And 2 into 2, 4 plus 1 into 1, 5. 2 into 4, 8 plus 5, 13. This is 6, 12, 5, 13. This is 14, 4, 13, 5. So AB is not equal to BA, even though they exist. Even if they exist, they are not equal. Okay. So this is the commutative property of matrices, non-commutative property. Then associative, as long as conformability exists, associative property holds. Matrix multiplication exists as long as they are conformable. That is, A times BC will be equal to AB times C. Okay, this is valid as long as conformability for multiplication exists. Okay. Next. Now matrix multiplication is distributive over addition. So A multiplied by B plus C is AB plus AC. See the sequence. If I do B plus C times A, it will be BA plus CA. Okay, this is distributive. Multiplication is distributive over addition. Then identity matrix. A into I is I into A is equal to A. Okay, if A is n by n, all right, not necessarily, but suppose it is 1 0 0 1. So, but generally this is valid for a square matrix, but you can have identity matrix with rectangular matrix also. Okay, suppose A is m cross n, let us say, then I has to be n cross n, and this I has to be m cross m. Then in this case this will be m cross m matrix. Did we understand? So identity matrix I is 1 0 0 1 or 1 1 1 m times and rest all zeros. So identity. Then inverse. Then inverse of a matrix. Of course, this is a big topic. We have to discuss singularity. Okay, if there exists such that if AB is equal to BA is equal to I, it is of a square matrix. Then B is called as the inverse of A. For that, there are certain rules to follow. Singularity condition, non-singularity condition, I'm sorry. So we'll discuss all that. Next. Okay, tell me this. If A into B is equal to 0, then what does it mean? Then what does it mean? If A equal to A into B equal to 0.
Any matrix should be null matrix.
All right, then. Okay, very important. It is not necessary that any one of them is null matrix. We will take an example. Say 2 2 1 0 0 2 1, okay, 2 0 0 1 0 0 5 4. None of these are null matrices, but when you do A into B, you see what happens. 2 into 0 plus 0 into 5 0, 2 into 0 plus 0 into 4 0, 1 into 0 0 into 5 0, 1 into 0, 0 into 4, 0. However, BA may not give you that. The 0, 0 multiplied by 2 and 1, you get 0. 0, 0 multiplied by 0, 0, you get 0. Then 5, 4 multiplied by 2 and 1. 5 into 2, 10, plus 1 into 4, 14, 0. So BA is not equal to 0, but AB is 0. Neither A is 0 nor B is 0. Okay. So you have to be thoughtful. So you may get a tricky question, a simple question on matrix understanding like this. So these are properties of multiplication. So equality we have discussed, addition we have discussed. Very important operation on matrix is transpose. Okay. So if A is an m by n matrix, then A transpose is defined as AJI n by m. That means A transpose is a matrix whose rows and columns are interchanged in the original matrix A. So this is 2, minus 1, 3, 0, 0, 3, 5, or 0, 4, 6, let us say. This is A. Then what is A transpose? The first row becomes the first column. 2, minus 1, 3. And then the second row becomes the second column. 0, 4, 6. Okay. So row and columns get interchanged. So there's a transpose of a matrix. And then there are properties of transpose. What are properties of transpose? A transpose holds transpose is equal to A. Now these are important properties, and again in various methods of solution of simultaneous equations. Now A plus B the whole transpose is A transpose plus B transpose. This is important. AB the whole transpose is equal to B transpose A transpose. And suppose we multiply with a scalar. K is a scalar. Then it is K times A transpose. All right. So these are properties. One important thing about scalar multiplication, which I missed here in properties of multiplication. I should have written here. See, K times a matrix A is same as you multiply every of its element with that K. That is the scalar multiplication. This we know. That means if 2 into 1, 3, 5, 7 will be equal to 2, 6, 10, 14. Every element will be multiplied. That is the scalar multiplication. So